Here's a picture of a shock absorber. We see shock absorbers in car suspension systems and on our mountain bikes. And we can diagram the behavior of a shock. Shock has a piston, and that piston is full of some fluid. The fluid could be liquid or gas. I think it's often gas. Okay, so if you try to compress this system, then the surface area of the cylinder and the piston has to push through this fluid. And at low speeds, that presents a drag force that's equal to negative BV, where B stands for the drag coefficient. On mountain bikes, I'm not sure exactly how the mechanism works, but there's a dial on the top, and you can change the settings, and you can effectively change the value of the drag coefficient. So a lot of shock absorbers not only present a force F equals negative BV, but they coil a spring. So the fluid, or the resistance offered by the fluid, provides something, a quantity known as damping in the system. So a spring by itself causes oscillations that are sinusoidal, and we refer to that as simple harmonic motion. A graph of damped vibrations, the result of compressing a spring that has the fluid resistance. That gives sinusoidal behavior, but sinusoidal behavior that decays away in time. So you might have a graph of position versus time that looks more like this. Now the frequency, in this case, we know if it represents a simple mass on a spring system, is the square root of k over m in radians per second. In this case, the frequency is equal to the square root of k over m minus b over 2m quantity squared. Okay, k, we know that's the spring stiffness, so that has to do with the properties of the coil spring. Mass, well, gosh, in your car, the mass is mostly the weight of the vehicle. The mass, in the case of your mountain bike, is mostly the mass of the rider. But in any case, we're all pretty clear what M stands for. And then B is the drag coefficient. And that depends on the viscosity of the fluid and the surface area of the piston that has to push through that fluid. If you have both of these types of force, the force from the spring, which is negative kx, and the force from the fluid resistance, negative BV, then we can write a differential equation based on Newton's second law. If MA is negative kx minus BV, then d2x dt squared is equal to negative kx minus BV. We can divide both sides of this equation by m. d2x dt squared is negative k over mx minus b over m times dx dt. Velocity is the first derivative of position with respect to time. Acceleration is the second derivative. Of course, x is just the original function. In other words, when something undergoes damped vibrations, position still varies with time, right? The position is still some sort of function of time, but whatever that function is that describes the position, when I take the second derivative of that function, it doesn't just give me back a negative constant times the original function, it also gives me a constant times the first derivative of that function. Second derivative, first derivative, constant, constant, and the function itself. So what type of functions have a first derivative that differs from the second derivative just by a constant? Well, how about a function like x equals e to some constant times t? Or x equals e to some negative constant times t, I should say. The first derivative, dx dt, is negative c e to the negative ct, and the second derivative is equal to positive c squared e to the negative ct. So these two expressions differ by each other just by a factor of negative c. In other words, the second derivative is the first derivative multiplied by a negative constant. I'm going to expect that whatever equation describes position as a function of time somehow involves an expression like exponential decay. And then we already know the type of functions where taking the second derivative gives us back a negative constant times the first derivative. Those are sinusoidal. So depending on how much math you've taken, you may have encountered a class in differential equations, and you know how to guess at a solution to this differential equation. If not, I don't have a problem giving you the solution right now. It's just x equals, well, it's kind of like the solution for simple harmonic motion, which is x equals a cosine omega t. It's just x equals something like a times cosine of omega prime t. And here what we have isn't just amplitude, but a decaying amplitude. So that's where the exponential decay comes in. This is a times e to the negative b over 2mt. And remember what omega prime is. Omega prime is the square root of k over m minus b over 2m quantity squared. So that's the solution to this differential equation that says d2x dt squared equals negative k over mx minus b over m dx dt. That differential equation is satisfied by this expression for position as a function of time. And when we graph this expression, then position as a function of time indeed looks like what we suspected. Sinusoidal behavior combined with exponential decay. The amplitude decays away as the system continues to vibrate. So it won't vibrate indefinitely. Eventually, the vibrations fade away to zero. Now, how rapidly they fade away to zero is referred to the amount of damping. You can have an overdamped system, underdamped, or critically damped. So I have a video, it's not my own, but I've copied and saved a video into this unit that shows resistive forces, a drag force that actually comes from the interaction of some magnets with a large piece of aluminum. Something known as Faraday's law of electromagnetic induction says if I take a magnet, I think in the video I have saved it's a disc magnet, and when the magnet moves in front of a block of aluminum, it induces electrical currents in the aluminum. Those electrical currents are called eddy currents, and you have some electrons that flow one way and electrons drift the other way. And as those electric currents are generated by the motion of the magnet in the presence of the aluminum, that wastes the kinetic energy of the magnetic disk and converts it into thermal energy as the electrons collide with impurities in the aluminum, and it slows the magnet down. So it's a form of drag force different than the fluid resistance you get in a typical piston, but it's a drag force nonetheless. And by adjusting the distance between the aluminum brick and the magnet, you can change the effective drag coefficient in this case. And that video demonstrates then the difference between overdamped, underdamped, and critically damped cases. So if I were to make a graph of a system where the B value is too small, then the system is underdamped, and it's just like the graph we drew above. The oscillations carry on for too long of a time. If your car suspension system is underdamped, if you were to hit a bump in the road, either a speed bump or a pothole, you wouldn't want to hit the bump and then have your car continue to bounce up and down as you drive down the highway. You would hope that your car suspension system is critically damped so that you just gradually come to rest before any vibrations occur at all. And in that case, we can say that there really are no vibrations, so the angular frequency for all practical purposes is 0. Now the only way that's true is if the square root of k over m minus quantity b over 2m squared is equal to 0, which would only be true if k over m is equal to b over 2m quantity squared. So in the case of a critically damped system, k over m is equal to b squared over 4m squared. We cancel one of the m's and we solve for b, and b squared must be equal to 4mk, or in other words, for the critically damped oscillator, the drag coefficient is 2 times the square root of the product of the mass and the spring stiffness. So back to the mountain bikes. If you have a mountain bike or you've ridden one that has adjustable suspension, you've probably seen, I don't think we can see it in this picture, but somewhere on the top of the forks or at the top of the suspension that controls the back of the bike, there's a lever, and by adjusting that lever, by clicking a dial, you can change the value of B. So let's say you loan your bike to somebody who's not as heavy as you. Then the value of M is going to go down. So I know the stiffness of the spring isn't going to change, right? So if the value of M goes down, then the value of B also has to go down to maintain the same critical damping. And likewise, if a heavier person rides your bike, then you have to increase the drag coefficient. So this represents critical damping, and this equation here, I should write it again, x equals ae to the negative b over 2mt quantity times cosine omega prime t, where omega prime is the square root of k over m minus b over 2m quantity squared, where k is the stiffness of the spring, m is the mass of the whole system, and b is the drag coefficient. So watch the other videos that I've linked on critical damping to try to get a more practical understanding of what this is all about. Thanks for tuning in. Our next lesson is about driven vibrations.